when we're solving polynomial functions, then what I need to do is basically write it in standard form. If it's not like, so assuming that you have some sort of equation where you have different things on, you want all your terms on one side and 0 on the other side. All right, maybe it starts off that way, but maybe it doesn't. In that case, the first thing you want to do is write it in standard form. Then you're going to factor completely. You're going to see if there's a GCF across all the terms. If there's not a GCF across all the terms, you're going to go through and you're going to factor by grouping. Just group them, the first 2 terms and the last 2 terms, assuming that there's 4. But you're just going to kind of group them one by one, or pair by pair. You're going to group them and factor the GCF from each group. Once you've done that, you should find that you have a bunch of common terms that you can then factor out all the way, and that's how we factor by grouping. So that is what we're going to look at right now. And these are in particular, these aren't polynomial functions, these are polynomial inequalities. So once we know what our zeros are, those are our solutions, but we also need to go through and see if it's an inequality, whether those endpoints are actually included in our answers or not. So I'm going to show you exactly what this looks like, and we'll also show it by graphing. But I want to start with an example so I can walk you through it. We're going to start with this one here. 2x cubed minus 7x squared minus 15x greater than or equal to 0. This is already in standard form. So what I'm going to do next is copy it over, and we're going to try to factor out a GCF. There's a common x in all 3 of these terms, but there's no common numerical factor. This is going to give us x times 2x squared minus 7x minus 15 greater than or equal to 0. Now that I've factored out the GCF, I'm going to look inside my parentheses and continue factoring. In this case, I'm going to have to factor with a diamond problem in a rectangle because I have a quadratic expression. On the top of my diamond problem goes a times c, which is 2 times negative 15, which is negative 30. In the bottom, I get my b, which is negative 7. And what I want to try to do are find 2 numbers that multiply to be negative 30, but add to be negative 7. So I'm just looking, because it's a negative 30, I'm going to have 1 positive and 1 negative factor. And I need those to add up to be 7. 30 is 1 times 30, 2 times 15, 3 times 10, and I think 3 and 10 is going to give it to us. If I did a negative 10, I do multiply to get negative 30, and I add to get negative 7. I use that to split my middle term into 2 factors, or into a sum of 3x and negative 10x. And that's what I'm going to sort into my boxes, giving me 2x squared plus 3x minus 10x minus 15. And now factor each row and column in order to determine the length times width of this rectangle. The GCF of the first row is just x, but of the first column is 2x. And I confirm that 2x times x is 2x squared. Then I'm going to factor my second column. The GCF there is 3. And I confirm that 3 times x is in fact 3x to get that top right corner. The GCF of the bottom row is negative 5. And I confirm that negative 5 times 3 is negative 15. So this means I have factored correctly because all of my pieces multiply up to be the same thing. And I can rewrite this as x times x minus 5 times 2x plus 3 greater than or equal to 0. If it was just equal 0, I would just go through and identify each of my factors that would make this product exactly equal to 0. Even though I am not going to solve it, I'm going to find an inequality. I'm going to identify the dividing points that are either solutions or non-solutions. The or equal to case happens when x is 0, x is positive 5, and x is negative 3/2. I know that because if I let 2x plus 3 equal to 0, I can subtract 3 from both sides, giving me 2x equals negative 3. And I can divide both sides by 2 to get that x equals negative 3/2. Those are all the numbers that make x exactly, or that make this entire function exactly equal to 0. But what I want to do are see all the places that this function is below 0 or is above 0. So I'm going to write down on the number line in order from small to large the different zeros of this function. And in order to tell if there's solutions where this function is greater than or equal to 0, I know that at each of these places in the middle, the function is exactly equal to 0. So I'm going to put closed dots on each of these points because I have or equal to. But now I need to see which of these regions between dots gives me a value that is greater than 0 if I were to plug it in. And I do that by testing some points in each region. I'm just going to pick a point for x, and I'm going to plug it into my little inequality here, and I'm going to check to see if it's greater than 0 or equal to 0. So from each region, like a number that's smaller than negative 3/2 would be like negative 2. A number between negative 3/2 and 0 would be 1. And I'm just picking the numbers that seem the easiest in each region. Between x equals 0 and x equals 5, I could test x equals 1. Here I can do negative 1, sorry. And for a number greater than 5, I'll just do 6. I don't know, it's larger than 5. And what I'm going to do is kind of test it in my little factored equation. You don't even have to know the number that it's going to equal. You just need to see whether or not the product is going to be positive or negative. And I'm looking for all the places that have a positive product. So for my test points, I get a negative x. I get negative 2 minus 5. And I get 2 times negative 2 plus 3. And I want to see, is it greater than or equal to 0? Well, negative 2 is a negative. Negative 2 minus 5 is negative 7. That's a negative also. 2 times negative 2 is negative 4. Plus 3 is still a negative. That's a negative 1. A negative times a negative times a negative is equal to a negative, right? Because the first two make a positive number, and then the last negative makes it a negative product. So I don't really care what this number is, but it's definitely going to be a negative number. If I wanted to see exactly what it was, negative 2 times negative 7 times negative 1 is negative 14. So it's, if you want to multiply them out, fine, it's negative 14. But either way, this is a negative number. So it's not included in my answer. If x is equal to negative 1, I'll get negative 1 times negative 1 minus 5 times 2 times negative 1 plus 3. This is a negative. Negative 1 minus 5 is negative 6. And this is times 2 times negative 1 is negative 2, plus 3 is positive 1. That answer is going to be positive. So this part of the solution is in my, this part of the number line is in my solution. I can keep testing numbers. If I test x equals positive 1, I get 1 times 1 minus 5 times 2 times 1 plus 3. And I just want to see if that's positive or negative. Well, this is a positive. 1 minus 5 is a negative. 2 times 1 is 2 plus 3, that's a positive. Positive times positive is a negative. And if you wanted to multiply those out, you could. That's just 1 times negative 4 times 5. So it winds up being negative 20. If x is 6, we get 6 times 6 minus 5 times 2 times 6 plus 3. This is positive. 6 minus 5 is positive. 2 times 6 is 12, plus 3 is 15, and that's positive. So the product is going to be positive. Which means that this part of the region is also in my answer. So my solution are just the places I shaded. From negative 3/2 to 0, combined with the region from 5 to positive infinity. If there's anybody that hated that method, there's another method. You're gonna like it. Just graph this on Desmos, okay? So I'm going to show you how we would do that. So all I really want to know is where is this function above the x-axis, right? Because that's where the function is positive or equal to 0. So what I'm going to do is graph this function, the original function just as it's written. 2x to the power of 3 minus 7x squared minus 15x. All right, so here's my graph. And I'm going to take a little screenshot. So I can actually write on this. Nope. Sorry, almost done. All right, and I'm going to paste this over here so you can see what it looks like. All right, this is a graph of the function, and it is literally this easy. Put a number line under your graph so you can see like what your x values are, where it's equal to 0. This is when x is negative 1.5, also known as 3/2. Right? This is when x is 0. And this one over here is when x equals 5. I can see where I'm just going to shade on here the places where my function is above the x-axis. Right? And you can see that it's from here on. Oh, no. You can see that it's from here on and in between here. And those are the same regions that we came up with before. Okay, so you can always just graph it and see if it's true. If you're wondering why I didn't do that first, it's because once you know how to graph it, like why would you pay attention to how to do it the other way? Right? But sometimes you can tell, like if you can just look at a polynomial equation and factor it very quickly, which sometimes you can, then it's easier to just kind of like reason it out. But honestly, you know how I feel about Desmos. I love it. I'm very pro Desmos. Just graph it, y'all. Just graph it and make your number line. It's fine. So here's another example. We're going to solve this equation. I chose this one because this is an example of where you want to write it in standard form first. To do that, I'm going to subtract 9x to the power of 4 from both sides. And that gives me x to the power of 6 minus 9x to the power of 4 less than 0. So I want to see where this function is below 0. I'm going to factor it quickly. I can see that I have a GCF of x to the power of 4. And if I factor that out, if I factor out x to the power of 4, I get x squared minus 9 less than 0. And I can, what I have here is a difference of squares. So a difference of squares has this rule. If I have a squared minus b squared, I can factor it as a plus b times a minus b, where the two factors are just like what was squared, because this is the same as having 3 squared for 9. All right. So from this, I get that my dividing points are my zeros. That happens when x equals 0, x equals -3, or x equals +3. I can put those onto a number line. And I can test a point from each region. You can also graph it, which we'll do next. I'm going to pick some test points. Oh, first of all, though, I'm going to write on here. These are open circles because I have less than, not less than or equal to. So these answers are not included in my shading. All right, and I'm just going to test points. I'm going to pick a point that's smaller than -4. I'll pick one that's between -3 and 0, like -1. I'll pick one that's greater than 0, but less than 3. And then I'll pick one that has x greater than 3. Like x equals 4. I test each of those in my factored equation only because it's easier to figure it out that way than it is to plug it into the original. That's why I'm doing it there. I get -4 squared times -4, or no, I'm sorry, -4 to the 4th times -4 squared, no, -4 plus 3 and -4 minus 3. I can do this. And I'm going to see if that's negative. Well, -4 to the power of 4 is going to be a positive number because that's -4 times -4, which is positive, times -4 times -4. Those two are positive, so it's a positive times a positive. So this is positive. -4 plus 3 is a -1. -4 minus 3 is a -7. All right, so positive times a negative is positive, which is not less than 0. Now I can test my other points. If I do that, -1 to the power of 4 is positive. Any even coefficient is always going to be positive there, or any even exponent there. -1 plus 3 is a positive number. Wow, I kind of wrote that funky. -1 minus 3 is a negative number. Positive times a negative is negative. So this part is part of my solution. If x equals +1, I'm going to go through here and test each of these in the same way. One to the power of 4 is positive. 1 plus 3 is positive. 1 minus 3 is negative. That product is a negative. So it's part of my solution. And the last number I have to check is x equals 4. Which I can do like this: 4 to the power of 4 times 4 plus 3 times 4 minus 3. And I would get positive times a positive times a positive, which is a positive. Which means that my solutions are just when x is between -3 and 0, and when x is between 0 and 3. Not including any endpoints. This is basically the region from -3 to 3, but not the exact point 0. So when I look at this on the graph, I'm going to expect that there's going to be like a curve that actually is tangent to the x-axis and only touches it at one point a couple times here. I know that's going to happen when I have my, oh, I put squared here. This is a 4. I know that that's going to happen when I have my x to the power of 4 that has that. It's just like a 0 and it has a multiplicity greater than 1. That means it just touches the x-axis there. But it's also going to happen at another point, I believe. Or I guess that only happens at 0. That makes sense, really, when I look at that. So here's how I'm going to graph it. I'm going to enter my function just as I see it, but in standard form. So I get x to the power of 6 minus 9 x to the power of 4. Yep, there, it just touches at that one little point. And I'm going to take a screenshot so I can write on this bad boy. And what you can see is if I make a number line here and I go over here and I put my open circles when x is 3, 0, and -3, open circles back again from the fact that my inequality is only less than 0, not less than or equal to 0, then I'm just going to highlight all the places my function is less than 0. It's all the way down here. Right, because like you can see this whole, like all of these parts, these are all underneath. I feel like I should pull this down a little farther. Like that. So you can see like all that is negative, so that's where I'm shading. Okay.